In this module, I'm going to discuss the running time of a flow-sensitive DFA vis-a-vis a flow-insensitive DFA. Now, it is common understanding and knowledge that a flow-insensitive DFA is faster than a flow-sensitive DFA, and we're going to try and dig this further in more detail on why this is so. So, in both cases, whether it's a flow-insensitive DFA or a flow-sensitive DFA, we use Kildall's work list algorithm to figure out which edges to consider for relaxation of the DFA value. Recall that even for the flow-insensitive DFA, where we maintain a global value, we typically proceed the DFA using the same work list algorithm so that we have a better shot at identifying which edges to consider for the relaxation. Now, in both cases, and when the other trade-off between a flow-sensitive DFA and a flow-insensitive DFA is, of course, the fact that a flow-insensitive DFA is less precise than a flow-sensitive DFA. However, we have also discussed that once we convert the program into SSA form, then a flow-insensitive DFA has equal precision to the flow-sensitive DFA, assuming all the quantities of the interest in this SSA form, in the DFA have been converted to SSA. For example, most IRs would convert all the scalars to SSA, and if the DFA is tracking scalars, then a flow-insensitive DFA will be as precise as a flow-sensitive DFA. Now, the maximum number of updates that a fixed point algorithm, data flow analysis algorithm makes or could make is basically number of program points into the height of the semilattice. And the argument here is that every update is going to bring the value some value at some program point, one step down in the semilattice. And because the semilattice is a bounded finite height semilattice, eventually all values will come down to the bottom value in that semilattice, and that would be the termination. That's the termination condition of the fixed point algorithm, and that has to be the termination condition. And so the maximum number of updates that can happen in a flow sensitive DFA is the number of program points into the semilattice height. Now, when I talk about the maximum number of updates in a flow insensitive DFA, in that case, there is only a single global value, and that global value can only go, for any update, it can go one step down in the semilattice height. And so you may be tempted to think that the maximum number of updates in a flow insensitive DFA is only h, which is the semilattice height. However, because we have converted the program into SSA form, the semilattice height has actually become bigger, because the number may have become bigger for most DFAs, because the number of variables has become bigger. And recall, for many of the DFAs, the height is proportional to the number of statements or the number of variables, and both of them increase when we convert the program to an SSA height. And in general, the number of updates that is still proportional to the number of program points into the semi-lattice height for the original semi-lattice on the flow-sensitive DFA. Even if you convert it to SSA and run a flow-insensitive DFA, the semi-lattice structure doesn't really change, and so the height remains similar. And so the maximum number of updates is the same in both a flow-sensitive DFA and a flow-insensitive DFA, and that's given by n into h, which is where n is the number of program points and h is the semi-lattice height of the original program. Okay, now we have already said that the maximum number of updates is order n into h. Now the question is, what's the time taken between two updates in the Kildall's work list algorithm? Now recall that when we run the Kildall's work list algorithm in a flow sensitive mode, then every time a value at a node changes, we add all the incident edges to the work list. So if it's a forward DFA, then we add all the outgoing edges to the work list, and then we check whether the values at the destination of those forward edges or the to node of those forward edges does that need to be relaxed based on the change at the from node of that forward edge. And if that node does not need to be relaxed, then we just remove it from the work list. If it needs to be relaxed, then we relax it and we add its forward edges to the work list, and so on, and we keep doing this. That's, recall, the Kildall's work list algorithm. So the maximum number of steps that you need to take in a flow sensitive algorithm between two updates is basically the typical degree, the number of incident edges to that node. For example, if the number of outgoing edges in a forward DFA from a node was 4, then at most I would take 4. I would do 4 different explorations before I hit one update. If none of those 4 had an update, then I would just I would declare that I have reached a fixed point. I will terminate the algorithm. But if there was supposed to be an update, then that update must be among those one of the 4 outgoing edges, and the maximum gap between the maximum amount of work that you have to do between the original update, which is at the from node, and the new update, which is at one of the 2 nodes, is 4, because you may have to look at 4 different edges before you actually get something that you wanted to update. If you are lucky, maybe the first edge that you looked at was needed to be updated, in which case it could be order 1. So in the flow insensitive case, the number of the time taken between 2 value updates is between order 1 and order D, where D could be the out degree or the in degree. I've written out degree and written this as DO because I'm just using a forward DFA as an example without loss of generality. If it's a flow insensitive analysis, however, then when we relax the value, and there's only one global value, then we basically add all the nodes, all the program points as part of all the edges in the program as part of my work list. And this is done because we don't know which other instruction in the program may be using the value which has been changed in this particular step of the DFA. And so in the flow insensitive case, the maximum distance between 2 updates can be again order 1 if we are lucky, or it could be as high as order n, which is the size of the program, because when something changes in a flow insensitive algorithm, we add all the edges or all the instructions as part of the work list. All of them need to be checked to be sure that we have reached a fixed point or not. And if we have not reached the fixed point, it's possible in the worst case that I have to look through n-1 instructions before I look at that particular instruction that was using the result of the newly updated value, and in which case the maximum amount of distance or time taken between 2 updates can be as high as order n in flow insensitive. So it seems like the amount of work that can, in the worst case, that has to be done between 2 updates is higher in flow insensitive than in flow sensitive. However, recall that we typically use the reverse post order for forward DFAs or the post order for a backward DFA to quickly identify the nodes, the likely nodes where we need, or the likely instructions where we need to relax the DFA value, and that actually is very, very effective typically. And typically the amount of work that you have to do between updating a value and then identifying another value that needs to be updated as a result of the previous update is typically order 1, and that's what I'm going to assume in the rest of this analysis. So although the worst case values are order out degree or order n, the time taken between 2 updates, the typical value is actually just order 1. Okay. Finally, we have already characterized the maximum number of updates. We have also characterized the number of the time taken between 2 updates. The third thing we need to characterize to be able to characterize the overall running time is the time taken by a single update. So recall that when we do an update, then we have, let's say we are doing an update across an instruction S, then we have some value, input value at the beginning of S. Once again, without loss of generality, I'm assuming a forward DFA. So we have an input value at the beginning of S, and we transfer it across S to obtain a transferred value in transferred, or I'm calling it in exfer, or in transferred, I'm going to call it. So I'm transfer in to in transfer. And then using in transfer, I update out, which is the original value at the out of S. And this update can involve a meet operation between in transfer and out. Now, the time taken by an update basically involves changing the out value from whatever it was originally to its new value, and that involves first transferring from in to in exfer and then applying it to out. And let delta be the magnitude of change between out and in. And this is the amount of work, I claim, that has to be done in this transfer, because after all, whatever was the whatever was the distance between in and out that much amount of changes need to be made at a minimum, because after all, some changes have to be made, and whatever is what the time taken to make the modification is at least proportional to the amount that the size of the change that has resulted from this transfer. Okay, so let's try to understand what the size of a change could be. So for example, let's say the transfer function for a statement S involves using the kill and gen sets, say x minus kill union gen. Then the size of a change is basically less than the size of these sets kill and gen for that instruction S, and this delta S is the distance between in transferred and in. It's not the distance between in and out. I'm going to come to that later. So I'm going to characterize the distance between in and out and divide it into two parts. One is the distance between in and in transferred, and another is the distance between in transferred and out. So if I look at the distance between in transferred and in, then that distance is characterized by by delta S, which is less than equal to in this case the sizes of kill and gen. And typically these sizes are much smaller than the program size. For example, for many DFAs, this size is just a constant for in 3 address code. For example, if I talk about liveness, then kill is just all the values that are defined in that statement, and gen is all the values that are used. And because it's 3 address code, these sets have to be small, maybe 1 or 2 size, because it's a 3 address code representation. Similarly, constant propagation would just require a constant number of kill and gen sets for every instruction. However, it's not necessary that these are constant. For example, for available expressions, we may kill all the values that contain a particular variable, in which case it can be non-constant, but even when they are non-constant, they are actually much smaller than the size of the program or the size of the overall set of possible values that this program, this analysis could produce. Okay, so we are going to go ahead with the assumption that delta S, which is the distance, the size of the change between a previous value of out and the new value of out, between the value of in and value of out, is actually delta S, which is the distance between the in transferred and the in, is small. Okay, now the distance between in and out, the change between in and out, is upper bounded by the change between in and in transferred and the change between in transferred and out. This is a standard triangle inequality. And we already have characterized the change between in and in transfer, which depends on S, and we call it delta S. And we have already said that delta S is typically much smaller for most DFAs than the size of the overall program. So the next question that remains to be answered is, what's the delta between in transferred and out? And that would tell us what is the time taken by a single update typically. So let's study this quantity the delta between in transferred and out. And we're going to discuss this separately for a flow sensitive analysis and a flow insensitive analysis. So let's first look at the flow sensitive analysis. In a flow sensitive DFA, the in transfer, so if there was an original value out, it's basically flowing through the entire program, and after flowing through the entire program, it may have flowed into in because of, let's say, some cycle or something like that, and that may have created in transfer. So the path between out and in could be pretty long, and because of that, all the deltas could have pretty much accumulated across this path, and so the gap between in transfer and out can be pretty large, because it may include changes due to many statements. And this is true for a flow sensitive DFA, because in a flow sensitive DFA we are maintaining different values at different program points. So for example, out and out next would be different by delta S, and then out next and out next would be different by another delta S, and so on. And all this can pretty much accumulate into a big value and a big difference, and that could show up in the delta between in transfer and out. And this could be as big as order n, or it could be as, depending on if the value size is small, depending on the DFA, the value size, which is the size of the maximum value. Of course, the change set cannot be bigger than the size of the maximum value. So you can say that this order of minimum of n comma value size. Okay, so why is it, once again, why is it n? Because after all, there could be up to n different changes. But if the value size is smaller than n, then the maximum difference, the distance between any two values, whether they are in transfer and out, cannot be bigger than value size. So we also use a min to denote that. Okay, but if I look at a flow insensitive analysis, recall that in a flow insensitive analysis, the out value and the in value are the same. There's just one single global value. And so the distance between in transfer and out is actually also upper bounded by delta S, because after all, out and in were just the same. And if the distance between in and in transfer is delta S, then the distance between in transfer and out is also delta S. In other words, even though there could have been a big path that the DFA transfers, the DFA traverses before transferring to in transfer, that the updates have been applied, are being applied incrementally across every statement as the DFA progresses. So we don't have, across a single update, we don't have a very big distance between in transfer and out in a flow insensitive analysis, unlike a flow sensitive analysis. So delta in and out is actually on the order of delta S, because we know that n equals out in a flow insensitive analysis. So in a flow insensitive analysis, the distance between the gap between the value update is small, it's local, it depends on S. But in a flow sensitive analysis, it could be much bigger, it could be global, it could be as big as order n or order value size, whichever is smaller. And that actually is a big difference between a flow sensitive and a flow insensitive analysis running time. That comes up as a big difference in the running time of the two analyses. Okay, so to summarize, the maximum number of updates in both a flow sensitive and a flow insensitive analysis is similar. It's both n into h, where h is the height of the semi-lattice of the original non-SSA program. The time taken between updates in the worst case is only out degree or in degree, depending on whether it's a forward analysis or a backward analysis in flow sensitive, and it's order n in flow insensitive. But typically, because of the partial order, the post order or the reverse post order, this is order 1. But the time taken by a single update can be as high as minimum of n comma value size, because it's a summation of all the delta s's. Whereas in the case of flow insensitive, it is only order 1 to say whatever is the maximum delta s for a given statement. And so the typical total time is basically obtained by multiplying n into h with the time taken with the single update, because if you assume that the time taken between two updates is just order 1, then the overall time taken by an algorithm is the number of updates into time taken by a single update, which in this case is n into h into minimum of n comma value size. And if I take the value size to be as big as n, then it can be as bad as order n square h. Whereas here it's just order n into h into delta s, and if I assume that delta s is constant size with respect to the size of the program, then this actually is order nh. And this is the reason why a flow insensitive analysis with SSA is typically much faster to do than a flow sensitive analysis without SSA. And that's one of the reasons why compilers or compiler developers prefer to use an SSA IR like the LLVM IR, because it allows faster analyses without you losing precision of those data flow analyses.